Everyone, welcome back. So let's try out a design problem with material science. Look at this and see how we can find the right material for our particular use case. So what do we have? We have a cylindrical rod that's going to be 100 millimeters long and have a diameter of 10 millimeters. Why this? Because it's just easy numbers. And it's going to be deformed using a tensile load of 27,500 newtons. So first off, it can't experience plastic deformation or have a diameter reduction of more than 7.5 times 10 to the negative third millimeters. So then it says which of these particular materials are possible candidates. So we have two conditions. First, plastic deformation. Second, diameter reduction. You can do these in any order. I'm going to do plastic deformation because that's the simplest one to figure out, and then we'll move on to diameter reduction with whatever's left. So plastic deformation means that I'm not going above my yield strength. So for this particular stress, whatever stress it is for this load, I'm just going to say testing load, is going to be less than my yield strength for that particular material. So let's go ahead and calculate what this stress would be when I have this 27,500 Newton load. So stress is equal to force over area. As I said in previous videos, whenever it gives you a diameter, it's giving you an area typically for these problems. It could be a volume, it might be saying it's a sphere. It said a cylindrical rod though, so it's an area. And so for area, that's going to be equal to pi d squared over 4. Okay, so what does that come out to be? Let's plug it in my handy calculator and find out. So pi 3.14 times 100, that's 10 squared, divided by 4. And I get 78.5 millimeters squared. Great. So now I plug this into my equation. So 27,500 newtons over 78.5 millimeters squared. There's another little handy tool. Remember that 1 Newton per millimeter squared is equal to a megapascal. You don't have to convert a bunch of times if you do it that way. That's why I like to do it that way. So 27,500 divided by that area comes out to be 350.3 megapascals. Okay, so any material that has a yield strength lower than 350.3 megapascals is currently out. So that means that aluminum with 200 is out. Brass with 300 is out. Steel and titanium, you are still possibilities. So now we have to move into figuring out the diameter reduction. Does either one of these have, or both, I mean, it doesn't mean any of these materials are going to work, but does either of these have a diameter reduction less than that 7.5 times 10 to the third millimeters? Well, how are we going to figure that? How are we going to connect it to what we have here? I have a stress, and I'll show you. So when I have this stressed, it goes from being this shape, it gets thinner. And so we currently have our load in this direction, which means that it's very easy for me to calculate my stress in the z direction, the long direction. But my diameter is not this direction, okay? My diameter is, in how we use our notation, that would be the x direction. How do I connect strains in different directions? Well, I use what's called Poisson's ratio. It's simply equal to negative my strain in the short direction over my strain in the long direction. So we can use Poisson's ratio, which is given, to figure out what my strain is in the diameter direction based on my strain in the z direction. Okay, so let's go ahead and do some math and figure this out. So first off, stress is equal to modulus elasticity times strain. We're going to do this for both materials, both steel and titanium. So 350.3, this will be for steel, and this is for titanium, is equal to 207,000, remember I multiply by 1,000 to go from gigapascals to megapascals, times my strain in the lengthwise direction. And it's the same thing for titanium, just a different value for its elastic modulus. So rearranging a little bit, what do I get as my strain for steel? Well, I get 350.3 divided by 207,000. That's going to be 0.00169. Okay, and for titanium, I get 0.00327. Now, right from this moment, I can already say that titanium is not looking good because it strained significantly more. And since it strained significantly more and their Poisson's ratios up here are fairly similar, titanium is the one that's the most likely to fail. Now, I need to check both of them because it could be that both of them fail. But titanium, I'm sorry, I'm saying doesn't look too good for you. Okay. So now what we can do is we can calculate what the strain would be in the diameter direction, and then from that, the change in diameter from that. So I'm going to do a little bit of algebra so I don't have to do quite so many steps here. I can just plug in my calculator one time, and we'll go from there. So first off, the strain in the x direction is equal to my change in diameter over my initial diameter. And so, since Poisson's ratio is equal to negative the strain in the x direction over the strain in the z direction, I can plug that in to solve for this guy. So, that'll be equal to, making sure I do this correctly, negative change in diameter over the initial diameter, strain in the z direction. And then finally, my change in diameter will be equal to negative my Poisson's ratio times the strain in the z direction. Let's see here. Yes, times my initial diameter. That looks good. So what I can do then is I can use this equation and I can plug in my values from earlier to figure out what it comes out to be. I have to zoom out a little bit here so I can actually see my Poisson's ratio. That works good. So first off, let's do it for steel. So that's going to be equal to negative 0.3 times my strain in the z direction, which is 0.00169 times 10. And when I plug in my calculator, let's see what I get here. I get a change of negative 5.1 times 10 to the negative third millimeters. So that passes. It is not more than the 7.5 we were worried about, times 10 to the negative third. Let's do it for titanium now. This will be equal to negative 0.34 times the strain, which is 0.00327 times 10. And when I calculate that one, it is equal to negative 11.1 times 10 to the negative third millimeters. And so that one does not work because it's too much. Max was 10.5, it's 11.1. So going through this, what we find out is that steel is the only one that has the properties we need. So steel is our victor in this particular design problem. So thanks for watching. Hopefully this helps you. And if you're not a subscriber or a member yet, please consider that. Every member I get helps me to continue making these videos and to keep on making content for you. Have a good one. Bye-bye.